Okay, we are 30. So very quickly, let's utilize this time that we have, and we screen not clear. Many people are stuck at joining. That's the current complaint. That is what people are saying. Joining, but others are joining now. Make sure that I think I sent 3 links. Some of them had problems. Finally, the one that I have sent is the one that has that is working. So you're saying that Purity is telling me that the screen is not clear. What about now? Is that better, Purity? Make sure we will share with them the link that is working, because some might be having an earlier link that was not working. Purity respond. My goodness. How is the audio now, everyone? Oh, it's not good to talk to people while talking. Okay, fine. We'll carry on. So we have talked about the idea of unit vector, and we have shown the ideas of Nyeri, Nyahururu, etc. Yeah. I think I'm getting enough good points now that it's working. We have also shown how to get the unit vector for a vector A. So we might say that unit vector is we have seen it is given by that. So we can now jump to the next subsection, which deals with vector addition and subtraction. And vector addition involves, you have 2 vectors, A and B. And of course, if you are like this one, you write something like a C arrow is equals to A arrow plus B arrow. So that is how you always observe that when it is in typed, it's in bold, when it is handwritten, you have to put arrow at the top. That is a requirement when you are doing vectors. Now, assume you have your 2 or one more thing. Let me confirm that I can see the video. It's okay. I'm just arranging my videos here so that I think we can just move on. So we have vector A and you have vector B. If you want to find vector C, which is the sum of the 2, you actually add the 2 scalars, A and B, that are sharing the unit vector, AY and BY that are sharing the unit vector, and AZ and BZ that are sharing the unit vector. And that allows you to have the final addition. If you are doing subtraction, you would have A minus B, and A, which is of course same as adding a negative. Therefore, you do the subtraction. You make sure that you are not subtracting or adding arbitrarily. You're making sure that you are matching the unit vectors that are respective to each of them. So having said that, let's assume that our A follows this direction and our B follows this direction. What that would mean is that if you want the sum of A and B, you actually have to add them using a parallelogram rule or head-to-tail rule that says that where the first stops, that is where you add the other one. So our B would actually come here, and therefore it is the starting where the A stopped. Therefore, the final one would be our C, which is the one that is joining the starting point of A and the end point of B. That is how we do the addition of vectors. And I hope our members are still joining, because I still see about 31 who have joined. I hope others are not having difficult joining. Okay. Vector addition. So we are saying that we follow the two rules, either parallelogram rule or head-to-tail rule, and vector subtraction still follows the same idea, except that if you are subtracting, you'd have to go the reverse of how B would go. So if this was our A that is going in that direction, and you go to, and this is B that goes in this direction, if you wanted to have A minus B, you actually now go the reverse of B, which is what opposite of that. Therefore, you now start at A, go to head of A, and then go to the reverse of B. And therefore, your final one gets at that point. That is how we do the subtraction using the parallelogram rule. And talking about the normal laws of commutative, associative, and distributive, we know that we can actually say that for a fact that addition follows commutative rules, and equally the multiplication follows the commutative law, because you can interchange the location of A or B and still get the final, the same answer. And we also say that they follow the associative law that says that A plus B or plus C with a bracket surrounding B and C, if that would be the same as A or B, A plus B, and then you add the C later. Similarly, it follows the distributive law, but which is, of course, you're distributing the scalar K into two vectors A and B, and you get the same result even if you you open the bracket or you never open. So this means that you can do this addition before multiplying with the scalar. So that is about, and of course, I think I should have mentioned this, that if you have a scalar K and another scalar L, and you have a vector A, you can multiply the scalars first and then multiply with the vector and still get the same result. So that is the associative, distributive, and commutative rules. Having said that, we can now jump to position and distance vectors, and say now that consider you have a point P in space or in the Cartesian coordinates, and then you are asked to find the position vector to this point P. What you do is that the position vector always starts at the origin. So you are saying that position vector, which is also called the radius vector of point P, is defined as the directed distance from origin O to P. And of course, we are saying that if you want to find this vector P, position vector OP, you'd have to jump to move from point P, you minus origin, and they might have X, Y, and Z minus O, which have X or 0, 0, and 0. And that would allow you to get the position vector. So just a second, I can hear someone knocking. I want to pause. Sorry for that, we can continue. So I was saying that this is how you get the position vector given a point in space. So you'd consider the point at the origin, and then the point the point itself, and from origin you go how many X units, how many Y units, and how many Z units. That gives you the position vector. But now you're going to see that in a better view, that if you have point P with the coordinates 3, 4, 5, and you are asked to get the position vector, you'd simply add the sorry, I think there's not one. So this would simply gives you that RP is equals to point P, which has 3, 4, and 5, minus point O, which is at 0, 0, 0, the origin, and this gives you the vector RP having 3 AX plus 4 AY plus 5 AY. So this essentially gives you the position vector of that point RP. But now assume that you have 2 points P and Q. The other thing that would be required, of course, the position from point P, you can get its position vector, which is from the origin as RP. And if you had a point Q and you want to find its position vector, you of course go back to the origin. What now we want to find is what we call the distance vector. Distance vector, it is indicated as RPQ, is the distance between point P and point Q. And I think in the next few paragraphs we are defining the distance vector. And I think here we missed here that this should have been a plus, not equal sign. So in your notes, you be sure to correct that RP is given by 3AX plus 4AY plus 5AZ. So having said that, those who are joining, I would actually ask you to rename your names or rename yourself to have the registration number at the end, because again at the end I will get this list and again share with our university. So you can always, you don't actually have to exit, you just have to click your name, rename, and then that will allow you to have the registration number on your name. So do you have any question regarding, okay, I think you have not finished with distance. So I think I'll show you the distance. And the distance vector is a displacement from one point to another. So this is where I was explaining the concept of P and Q. Point P and point Q. You want to find the distance between them. The distance between them is the one that is indicated by the distance vector. And the notation for that is R with an arrow at the top, then PQ. This illustrates it is a distance from point P to point Q. And simply the displacement from one point to another. Notice that this is not equals to, I have said it is not equals to RQP, because vectors are directional. And if they are directional, that means one moving from point A to from point P to point Q is different from moving from point A, from point Q to point A up, point P, sorry. Okay, so having said that, we can move on and say that this is how we have defined the distance vector as being equals to RQ minus RP. So if you are to do this mathematically, you'd actually need to get the coordinates of Q and you minus the coordinates of P for each respective unit vector. So assume, but I think we don't even have to assume that there are going to be sufficient examples coming down here. So all we need to do now is to carry on and say the following. The difference between point P and vector A should be noted. Though both P and A may be represented in the same manner as X, Y, Z or A, Y, A, Z, AX, A, Y, and AZ respectively, the point P is not a vector. That's what we are saying, that only its position vector RP is a vector. Okay, I'm receiving comment from Kibet Isaac. There is telling me that the audio is smooth, there is no buffering, and we can be using Zoom in the future. Please check out screen sharing because it is not clear. screen sharing is not clear. That's a good point. Tell me, how is it now? Well, that is Kibeta is telling me. Kibeta, respond very quickly so that we move on. I've changed something on my site. Tell me if it is better. Oh, it's fine. So it is better. I think, okay, now it's better. That is from Brian Morene. Thank you very much, Brian. So we are talking about that we want to differentiate a point that is represented by X, Y, and Z, which might be something like 3, 4, and 5. This, we are saying it is a point. This is a point, not a vector. But a vector would be RP, which is represented by 3AX plus 4AY plus 5AZ. This is a vector. So that is the distinction that we are getting from the position and its point. Vector A may depend on point P, however. For example, if A is equals to XY, Deji, I'm the one allowed to have video. Only me, not anybody else. So mute your video and only in audio. Just watch what you are saying. Okay, so vector A may depend. Okay, so you're saying that vector A may depend on X or on P. For example, if A is given by 2xy ax or y squared ay minus x squared xz squared, and P is given that, then A at point P would be given by this. I think I have highlighted where you may not be able to see. So let me do it up. Yeah. So what I am saying is that A may depend on P, and therefore this equation may change from being equals to this, but at point P it becomes something else, which is that a vector field is said to be constant or uniform if sorry, that was an interruption. A vector A may depend on point P. For example, A is equals to that, and P is equals to that. Then A would be given by this. They're saying that a vector field is said to be constant or uniform if it does not depend on space variables X, Y, and Z. For example, B is equals to this is uniform, where, so you can see this one does not depend on space variables X, Y, and Z. Therefore, if you have a vector that takes that form, you see that vector is constant. But, if it depends on space variables like X, Y, and Y squared or Z squared, then you see that it is not uniform, but rather it is varying from point to point. Okay. This guy, we told him to mute him, move the video, but he didn't. So what do you do with him? Tell him to don't show the video. Just mute your video, Gideji Joseph Kariuki. We don't want to spend time looking for you, and yeah, thank you. My video is the one that is on the picture. All right. So here's an example that we can do, and probably we should do this without. We should do this so that we make sure that we are able to know what we are doing. Oh, no. Did I put full screen here? Then I'm not able to remove the full screen. I'm struggling with many things, so no problem. Now I've shared screen, but it's not able to minimize. Okay, can move on then. Yeah, I got it. So I wanted to open something here that allows us to do some mathematics. And just a second, good people. So I wanted to do this example with you so that we can see how whether these concepts we got them. So okay, so this is the problem I want us to solve. I know you may have these notes on your side, but we can see if we can do this. So the question is asking if A is given by this and B is given by this, we want to find the component of A along AY. And the other thing that we want to find is the magnitude of 3A minus 3B. And how do we do that? So the first point is find the component of AY along the component of A along AY. And you're told that A vector is given by 10AX minus 4AY plus 6AZ. So if you are asked to find the component of A along AY, you just pick the unit vector A and you identify that minus AY is equals to minus 4. That is straightforward. You don't have to think about it. Just pick the scalar of the unit vector AY. Now that is part A, and you want to do part B. The question is asking the magnitude of 3A minus 3B. The magnitude of 3A minus 3B would be 3 times 10AX minus 4AY plus 6AZ. Then you say minus B. Oh, sorry, I think I should. B is equals to 2AX plus AY, and the component of AZ is equals to 0. And of course, if you ask for the magnitude, that means you do this. This simplifies magnitude. So what do? You first of all work out this one that becomes 30. You can say is equals to, I think I can put a line between here, is equals to, I can put AX before so that I perform this subtraction, which is equals to 30 minus what? Minus 2. Then I can say plus AY. Then I say this minus that, which is equals to minus 4 minus 1. Then you add AZ, which is equals to 6. If I miss anything, you can always put it on chat. Therefore, I will be able to know how we are faring. Okay. So this would come to AX 28 plus AY minus 5 plus AZ 6. And of course,